Okay, well, Hall and Trunkel here, going to teach you about oscilloscopes. Majid on camera, good man Majid. Let's make some art. Okay, so this instrument here is an old school oscilloscope, and if you know how to use this, you'll be well prepared to use the more modern digital oscilloscopes. The first 2 weeks of our lab, we'll be using this extensively. So, what does this thing do? Okay, I'm going to turn it on, and you'll notice that there's a green line comes up here eventually. There it is. Was like that. This is a voltmeter. It's a voltmeter for time. Let's see what we mean by that. I'm going to turn this knob here, the seconds per division knob. You'll notice that the screen is divided into divisions. The seconds per division knob or the time knob tells you concerns the horizontal scale. I'm going to turn this to 10 milliseconds per division. That means that there's a beam. Oh look, there it is. 50 milliseconds per division. There's a beam that goes by and it takes 50 milliseconds to go from one division to another. So that means in 10 divisions it takes 500 milliseconds, which is a half a second. So this goes by twice a second. 1, 2, 3, 4. You see, so this beam goes by twice a second. How does that happen? I'm going to tell you now. There's a beam of electrons generated in the back of this thing. And electrons are really light and easy to change their direction because force equals mass times acceleration. It's really easy with a small force to accelerate these electrons. And they pass between two capacitor plates, and the voltage goes slowly positive, pulling them to the left. It goes slowly positive, then back to zero. Positive, back to zero. So it's a ramp voltage. If you were to look at voltage as a function of time, it would slowly increase, then drop down to zero, slowly increase, and it'll do that per sweep. And we can control that voltage signal that happens inside the oscilloscope with this knob here. Okay, so let's see what I meant by voltmeter. The uppy-downy scale is volts per division. Right now I have it at 0.5 volts per division. So I'm going to put it now at 2 volts per division. If I put into this BNC connector, if I put in a voltage difference between the outside and the inside of 2 volts, this will be deflected by 1 division because it says 2 volts per division. Again, what's going on? It's the moral equivalent of what's going on for the horizontal deflection. There's 2 plates, the beam comes between 2 plates, and your signal of interest controls the voltage across these 2 plates, and you can deflect the electron beam up or down. Let's deflect the electron beam up or down with this 9-volt battery. I'm going to hook up a BNC cable. This is called BNC. I'm going to shove in the BNC cable in here, and I'm going to put the alligator clips. I'm on channel 1, okay, that's good. And I'm going to put these alligator clips to the outside of the battery. This is a 9-volt battery. Now, when I do this, it went up too high. Oh, it's 9 volts, so it goes up 4 divisions.
So change it to 5?
Yeah, change it to 5 volts per division. And this will jump up 2 divisions. See? Up. Up. Let's make it go by even faster. Now look at this. I can make a square wave by tapping. Look, I'm on, off, on, off, on, off. And so the voltage between these 2 alligator clips is 09090909, bouncing up and down like that. Okay, so that's kind of how you make a square wave. Except obviously it's not how you make a square wave. You make a square wave with electronics. That's a signal that I was generating. We have an electronic signal generator or a function generator. That's why this is called a function generator. It generates functions. Functions of voltage is a function of time, that class of function. Let's turn this guy on, and this is what, yeah, we're going to do this next, right?
Yep.
Okay. So we're going to turn this guy on and we're going to look at what comes out of this guy. To some extent this is like software. You can tell by reading the labels on the knobs what the stuff is. It's like reading the pull down menus on a piece of software. When I stick this in here, I'm going to have 1K, that's 1,000 hertz. A hertz is how many times per second. So 1,000 times per second, there's a picture of a triangle. There's a triangle going to happen. So I better stretch this out there. So if I want to see something that's 1,000 times a second, well, if I have 1 millisecond per division, then you'll have 1 division from here to here. That's good, I can see it. So this is a, yeah?
I just wanted to point one thing out. Some people think when they first look at the oscilloscope that when you change this voltage per division knob, you're actually changing the size of the signal. That's not true. That's just changing the display, meaning how many volts are each vertical square representing. If you want to change the actual size of the signal, you want to change the amplitude knob. So you can see as if I decrease that knob, the signal gets lower, and if I increase that knob, it gets bigger. So the signal generator is actually controlling the amplitude as well as the frequency, where the oscilloscope is simply for display only.
It saves you a walk. When you do this, it saves you walking up to get a closer look. You see, I'm kidding. Okay, so we can change the frequency with this knob. There's a multiplier. 1K times 1 is 1,000. 1K times 1.4 is 1,400. It's 1.4 times 1K. So we can change the frequency. We can also change the shape of the oscilloscope. This is a sine wave. I'm going to stretch it out. I haven't changed the frequency. I've just changed how much of the signal, how much time I represent on the screen. Now, we're talking about triggering now?
Yeah.
Okay, so now the question is this. Here's a signal that's happening 1,000 times a second, right? The oscilloscope it starts redrawing this picture. You have to time when you start redrawing it to get a nice crisp picture. I'm going to move the position of the signal over to here. See, I can move it lefty-righty, or I can move it uppy-downy. You move these to suit yourself. We want to talk about when the signal starts. That's called the trigger level, the level at which I'm going to start drawing the picture. This says level. Now look here, as I turn this knob, it starts at a higher or lower voltage. Supposing I wanted to start, say, at 0 volts, I'll put it there at 0. I'll explain how I know this is 0 later on. Now, so every time the signal is 0 volts and increasing, then that's when I'll do it. This is a slope knob. I can say trigger on a decreasing voltage. Every time I do that, every time you pass the same value and you're decreasing, then trigger. So that's called triggering. Signal generators come with their own trigger signal that you can look at. So we have a 1 kilohertz signal sine wave. Well, actually, this guy here has an internal clock that makes a square wave of the appropriate frequency. And this is very handy because I can put this into this junction here in the oscilloscope and tell the oscilloscope, don't trigger off whatever I put in channel 1. That's what I'm doing now. The source is channel 1. I can say trigger off the external source if I put it in here. You often have to do that, but that's for later. Okay, now what we're going to do? Now we're going to do calibration. I said that well, this is a 9-volt battery. How do I know it's a 9-volt battery? Well, I put on 2 volts per division and it jumped up 4.5 divisions. I don't know if that's right. So let's calibrate it. So most oscilloscopes have an internal signal, an internal square wave. This guy here is our internal square wave. So I'm going to put the positive lead here. And he says 1 kilohertz, 500 millivolts peak to peak. Okay, so I'm going to adjust a position where it's convenient for me. I'll move it over. Now I'm going to increase it 500 millivolts peak to peak. That means that's a half a volt. So if I put in 0.1 volts per division, my signal should be 5 divisions high. And let's see, I can turn this, I can calibrate this so that I have my signal 5 divisions high. And there, that's it, that's good. Now, it's 1 kilohertz, that means 1,000th of a second is how long it takes to start its cycle again. And so at 0.2 milliseconds, I should be 5 divisions wide. So let's see, I've got to make this 5 divisions wide. And there, I'm twisting this knob, this one here, and I've just made it 1, 2, 3, 4, 5, a little bit off there. That's 5 divisions wide there. I'm going to move it over to see. Good. So now it's calibrated. I don't touch these knobs anymore. Now there's something else you can do. It says the signal here, it says DC. That means measure the absolute voltage with respect to ground. And I can hit the ground. That's my 0 point there. So look, I know now that whenever the beam is on that line, that's where 0 is. Oh, so this was going from 0 to negative half a volt. That's interesting, I didn't know that. Okay, and there's also an AC button here. What that does is it subtracts a constant offset. You could have a fluctuating voltage that goes from 1 volt to 3 volts, 1, 3, 1, 3, 1, 3, 1, 3. If you put it into the DC, if you had a button on DC, you'd see the line going from 1 to 3 to 1 to 3. If you put it on AC, you'll just see it go from minus 1.5 plus 1.5, minus 1.5 plus 1.5. It'll subtract the constant output.
Well, I have a question. Why don't you have the ground wire connected to anything from that connector?
That's a bit confusing. Okay, we should make a comment on grounding, right? When you have a building, if you go to the outside of your house, you'll find somewhere outside your house there's a large metal bar hammered into the ground, and there's a wire going from that bar into your house. That's called ground. So the outside of any of these devices is called a chassis. So this is a metal chassis. If a wire that was connected to the electric cable touched this chassis and you touched it, you could get a shock. So what there is there's a solid connection, there's a solid metal going from this chassis all the way to that big metal rod stuck in the ground. That's called grounding. The third fat pin on the 3-pin plug is to achieve this. So anything that's touching ground, it should be at the same potential, and that potential should be 0. 0 volts with respect to the ground. So any uncovered external metal you see on a device will be at 0 volts with respect to the ground. So when I plug in the BNC cable, this metal here is at the same voltage as the outside. So if I got a voltmeter and pull it from here to here, I get 0, or from here to here, I get 0. But this is at the same potential as that because that's just the way these cables are made. So I actually don't need this cable. It's a little bit subtle, but you'll get used to it. I mean, as the months and years go by and you're using these devices, you'll get used to the notions of grounds. There's one more thing we wanted to see, right? What happens when we zoom in on the voltage? Right. Look, I'm going to take this. I got no signal now. I got no signal, and it says 0.2 volts per division. Oh, what's this? There's something fluctuating. Oh, and look, it fluctuates, it changes wildly, depending on what I'm doing. I put this here versus here, look. Oh, look at this.
Oh boy.
Oh boy, what's going on?
Crossing the beams or something.
There's something crazy going on. Oh man, look, I'm triggering on it. Look, without anything going in, I've got this. So let's see what's going on. We have 1, 2, more or less 3 divisions. At 5 milliseconds, we've got 15 milliseconds per division. That corresponds to the question is, what frequency is this? How many times does 15 milliseconds fit into a second? Around about 60. This is the 60 hertz AC signal that powers all our power points on the wall. So it's bathing us in radiation. You raise your hand. If you raise your hand, or actually stop touching it. Now touch it. Put your hand up. It got a little bit bigger. You're an antennae and you're picking up this 60 hertz radiation, and this is bathing everything we do. So you're gonna, before your career as a physicist or an engineer at the University of Scranton is done, you're gonna have to deal with eliminating the 60 hertz noise that's everywhere. Okay.
One last thing, right? That was it, right? One last thing. If you show up and your oscilloscope doesn't seem to be picking up a signal, if you want to zoom in, Majid, you're going to want to make sure certain things are, certain knobs are pushed the right way. Under here, source, you're going to want to make sure these connections are all the way up. You're going to want to make sure the trigger choice is all the way to the left. And then again, check that your DC here, and that this is pushed to channel 1. I think that's it.
That's it.
Okay, there we go.
Happy oscilloscoping.
See ya.